Thank you very much, everybody, for attending this Thermal Transport Cafe. This is the fifth year that we've had this initiative. This is my second year being involved in Thermal Transport Cafe. It was originally developed by Professor Matteo Bucci and MD Rahman at University of Texas, El Paso. So for today's inaugural seminar for the fifth year, we have Dr. Yutaro Umehara. So Dr. Umehara is an assistant professor at Kyushu University. He did his PhD at University of Electro-Communications, also in Japan from 2019 to 2022. He mainly worked for his PhD on quenching phenomena from various aspects, mainly experimentally, if I'm not mistaken. He was directing the thermal energy conversion lab, and his current work now focuses on kind of similar things, but also enhancement of critical heat flux and improvement of onset nuclear boiling and quenching characteristics. So we're very honored to have him speak for today, and I will leave the floor is all his. So thank you very much, and thank you to Dr. Mihara for his time.
Thank you for kind introduction. So I'm Yutaro Umehara, and working in the Kyushu University as assistant professor. Today's presentation and title is expanded clarification of quenching phenomena. So firstly, I'd like to introduce briefly myself. Okay, so this is my self-introduction. So yeah, I started the research career from 2017. Before started this career, I focused on the playing football, yeah, in a college football. But after that, so I focused on the research only. So, and started the research from 2017, and this is my master degree. I studied abroad in the University of Michigan in the nuclear engineering department, and supervisor is Prof. Sheldon. And after that, I started to my PhD degree for the doctor course in UEC, University of Electric Communication in Japan. So it's my university is like a small scale in a small town in Tokyo, but currently the totally different situation. And Kyushu University in Fukuoka is we can see the so many uh forest, and sometimes we can see some animal. It's a very great nature situation. So, but I still focus on the thermal engineering. So I started to from this question in today's seminar. What happened when the 1,000-degree metal is immersed in water? So when the 1,000-degree stainless steel rod immersed in 80-degree water, it's firstly this kind of a situation. So film boiling. So paper film covered all the surface. So this condition is heat transfer coefficient is very low due to the no liquid solid contact. So after that, and a paper film is peeled off from the bottom surface, bottom of the rod thread, and then nucleate boiling occurred in the middle part here. So the cooling curve is like this. This part is a film boiling phenomena, and after that, then a nuclear boiling phenomena. So this is a basic idea. Okay, so the first topic is this one, quench phenomenon in non-fluid. So non-fluid and the particle is dispersed in the distilled water or oil or something. And we made it another fluid by using the ultrasound wave to disperse it in another particle in the liquid. So finally, we made a kind of nanofluid. This one's a titanium and alumina and silica. So the nanofluid is a very good, very nanofluid can enhance the various heat transfer mode, such as critical heat flux. And this one is a full boiling case, and here is a bare surface. But when we use nanofluid, we can enhance the CHA. Now also in the single phase flow and some conductivity increasing. And the quenching phenomena, also the nanofluid can enhance and quenching phenomena, and then we can reduce cooling time by using nanofluid. So the next video is focused on the quenching phenomena in a silicon nanofluid. Okay. When 1000 degree stainless steel rod immersed in the silicon nanofluid, the first initial condition is film boiling. Almost it's same, and in the water case, and the paper film is covered on the surface. But after that, suddenly the paper film is collapsed to one point, and then the small bubbles are generated from the outer surface. So the cooling curve is like this, and a film boiling condition, and then after that, suddenly cooling rate is enhanced. So this is a research question: why this phenomenon is occurred in a nanofluid? So the reason is a surface conditioning. So now before the quenching started, is like this stainless steel rod, but when we repeated the test and heating up and cooling down, and heating up and cooling down, and we repeatedly, the surface condition is also changed. So nanoparticle layer is deposited on the surface. So during the boiling case, in here. So nanoparticle is dispersed in a liquid, and when during the cooling case, and a bubble is coming out from the solid, and nanoparticle is aggregated in the very liquid, thin liquid film layer, and then nanoparticle layer is formed. So when we repeated the test, nanoparticle layer is formed is like this. So the main reason of the some reason of the requenching phenomena is nanoparticle layer. But why nanoparticle layer can enhance can reduce the cooling time? So this is one mechanism. When a bare surface case, during the film boiling case, and a bare surface and sometimes liquid solid contact occurred, but the heat coming from the inside in a high temperature surface, and then liquid boiling occurs, and then paper films is come back. But when we apply the nanoparticle layer on the surface, liquid solid contact occurs, but heat it doesn't come so much due to the nanoparticle layer is a low semiconductivity. So and then the liquid solid contact is longer than the bare surface cases. Finally, and the kind of small bubble or pinpoint is collapse. So the mechanism is low thermal conductivity of a nanoparticle layer, and also increase the thickness is the main reason. Finally, this thickness and the low thermal conductivity of a nanoparticle layer restrict the heat from the metal inside, and then finally, we can get low contact temperature. This is the main mechanism of the reduction of the cooling time when we use the non-fluid. The contact temperature is like this. Here is sample conductivity. When we get the small value, finally we get low contact temperature. And this low contact temperature induced RE quenching. Okay, so that's a little bit change of the topic, quenching phenomena in Japan. So Japanese salt is really important the quenching phenomena. Okay, maybe someone knows this in Japanese salt. Maybe Japanese salt have some pattern and in this side. So this pattern is made by the quenching phenomena. When we make the Japanese sword, we added the clay on the surface. This clay is very important to make the pattern. So this clay is like a nanoparticle layer. They have a very low thermal conductivity, so they can induce the rapid cooling. But they didn't just make the paste. They added some pattern on the surface. This pattern is very important to make the pattern of the sword. So, and also they choose a different material on the surface. So, and this one, a red one is the same one, but they made some pattern. So after that, they choose a different gray and a different side because spine side is maybe need a toughness, but in braid side is a needed tough, no, hardness. So they choose a different semiconductor gray added on the on the sode. So and then also they change thickness to after that they heated up the Japanese sode to 1000 degrees C, and then they quenching in a water bath completely. So this quenching phenomena is very important to make great Japanese salt, and also this pattern on the surface pattern is very important. Is some gray pattern is very important to make this pattern on the salt. Okay, so this is a quenching phenomena in Japan. Okay, let's move to a different topic. Okay, so this one is a correct recent research result on the quenching phenomena in a cryogenic. Okay, so cryogenic fluid application we can find everywhere in the various industry field. So such as superconducting magnets with the treatment and the feed food or something like that. So especially in a liquid fuel rocket also need to use cryogenic. So also here is a image of the SpaceX engine, and here is a liquid oxygen and liquid methane. Also there the cryogenic. So they need to transport from the tank to here. Maybe in a pipeline need to cooling down to the saturation temperature of cryogenic. Now also they need to cooling down to these components, all components to the saturation temperatures. So they need to spend so much waiting time for the fill time of fuel. Now also they need to use a large amount of the consumption to cooling down each component. So that we need to uh, improve the cooling condition for some surface modification, something like that. So, on a previous research reported to improve the rapid cooling method, improve the cooling duration, and when they use the cryogenic, so they reported anodic aluminum oxide, and this is aluminum substrate. They added the anodic oxide, and this nanoporous layer is very important to enhancement of the cooling phenomena. So this is the bare surface case, and a cooling curve. It's like this. And this is the boiling curve. It's like this. But when we added this AAO surface, we can reduce the cooling time and 46%. And the boiling curve is in the here. This point is moved to the higher temperature point, and this enhancement rate is 45% enhancement. So they reported about the mechanism of this is based on the contact temperature. Also, amino and the AO surface and the totally different than the contact temperature because AO surface AO is a porous layer, so they have low thermal conductivity. That finally they can get this kind of low contact temperature. So they reported this is the main mechanism of the rapid cooling. But our research proposal is to develop the different way to rapid cooling technique by using the copper porous plate. So this one is a copper porous plate. And this copper porous plate can enhance the critical heat flux. They also try to use to improve the cooling phenomena. This is the same image. This part is porous part. And also they have a big pore in the surface. So we try to use this one to enhance of the cooling characteristic. So this is how to make up the copper porous plate. So we use a electro deposition method. So this method is usually use plating method when we cover the metal by using the different same metal layer. So it's usually when the plating method case, they apply the very low current, uh, but our case we applied a very high current. So finally we can get hydrogen bubble from cathode and the anode like this. The cathode in the copper flake is deposited on the surface, and also hydrogen bubble coming out from this cathode. And then finally, we get kind of a copper porous plate. So this one is a actual video when we making the copper porous plate. So hydrogen bubble is coming out from the cathode, and so finally we get this porous plate. So we apply this porous plate for the sample. So this is the experimental process. It's very simple. And this is a dual bottle and the liquid nitrogen is poured in here. And we use a couple block for the experimental process, test specimen. And then the dual bottle is a flat in the bottom surface to visualize quenching phenomena. So the schematic design is like this, and we inserted a two thermocouple in the middle part here and here. So and then during experiment, we immersed depth is a 2 or 3 millimeter, and here we immersed, and then we added the copper porous plate on the bottom surface, and we're using a soldering adhesion. And then we calculate the board temperature and the ball heat flux from the inverse by using the inverse analysis, and we use a Laplace transformation to calculate the board temperature and ball heat flux. So here is a experimental result, and this temperature and the time, and the bare surface case is like this. We spent almost 30 minutes to cooling down to the saturated temperature of liquid nitrogen. So and then next one is here. This one is a copper plate. We just added a copper plate. The thickness is 1.5 millimeter, and it's like this. In this case, we can reduce the cooling time at 40% reduction. And then we added the different copper porous plate and like this. We change the deposition time of to make the copper porous plate and 3 minutes and 5 minutes and 7 minutes. When we increase the deposition time, also the thickness increase, but porosity doesn't change much. But this one is a very good result, and we can achieve the 90% reduction of the cooling time. Okay, so the copper plate case, maybe in this age, have some effect to reduce the cooling time, unstable film boiling due to sickness. But copper porous case, the thickness is thinner than the copper plate, so maybe this effect is not so much. So maybe have different effect to improve the cooling characteristic. Okay, the next is a boiling curve, heat flux and force heat flux. And the black one is a bare surface case. And this brown one is a plate. So the heat flux doesn't change when we add this copper plate case. But when we immerse the test specimen, with couple pores, we can see the high heat flux when just immersed when it started just started the case. Very high heat flux we can see, and then the next point is this point, and the high wall heat flux case, and the bare surface is a very low heat flux, but in the other one is a couple pores case, very high heat flux as it shows. So this 2 point is very important for to reduce the cooling time. Okay, the next one is a high-speed image of during the quenching. This one is just copper plate and around 28 Kelvin. Please see. It's like this, very smooth film boring, and paper film is covered all surface. The next one is 6 ampere 3 minutes deposition of the copper spray. It's like this, 28 Kelvin point. So not smooth paper film. We cannot see any smooth paper film. Some point is a liquid straight contact occurs, and then the paper film coming generate, and then but repeatedly in the liquid straight contact, paper film cover, liquid straight contact like this. So it's a expanded image like this. So some point is liquid straight contact occurs, and but after the suddenly coming out paper film. So not stable film boiling, but some duration they have some film boiling point. So we try to understand why the mechanism of this air quenching in a rapid cooling, and when we use copper phosphate. So this one is a property of the copper and the copper phosphate and the liquid nitrogen. So based on these properties, we calibrated the contact temperature. So in a copper case, and contact temperature is 35 when the initial temperature case. But when we use a copper phosphate, the contact temperature is very low. So that is this low contact temperature maybe have some effect against the rapid cooling. But when we use a different deposition time in 3 minutes and 5 minutes, a minute, it's also the cooling time is a little bit changed because this heat flux is a little bit enhanced. So the next question, how does deposition time affect the rapid cooling? So when this one is the same image when we make the different deposition time. So the pore size a little bit change, but thickness is also a little bit change. So maybe various surface condition also change, but we focus on the wickerability of the surface. So we measure the wickerability. Wickerability is when we attach the capillary tube on the surface, this liquid level is changed due to the capillary force of the copper force. So this speed and time change, and we measured, and then finally we get this value. This is the body flux, and then finally we get this wickerability value. So this is the result, wickerability and the deposition time. So when we increase the deposition time, also wickerability a little bit increase. So this one is maybe have some effect to improve the this after the quenching and this high heat flux, high transfer coefficient in the during the high wall superheat range. So this is a summary. When we apply the copper phosphate to reduce the quenching time, so an aquaphor sprayed can achieve the 90% reduction of burn time. So because the summer conductivity led to low contact temperature. And finally we can get lady boiling transition. And also the boiling time affect the boiling at cooling time. because maybe weakability have some effect to reduce cooling time. Okay. So next topic is a final topic. Today's seminar. So quenching phenomena near liquid film front. So it's when we force down to liquid film along the high temperature wall, it's like this. When liquid film, it's like this. So we capture the actual summer hydraulic phenomena by the high-speed camera, like this. So it's a boiling occurred near the vigorous boiling occurred near liquid film front, but and here and done so much, just boiling occurred in the front. So how do you predict this falling velocity of the liquid film? This is a research question. But we need to show some research background. So emergency co-cooling system in a nuclear power plant. So, and this is a nuclear reactor and in a pressure vessel. And sometimes on emergency situation, severe accident occurs and liquid fuel is vaporing out. And this one, the nuclear fuel is it's coming out in contact to the air. And at the time, we need to emergency cooling, co-cooling system needed. So in that case, the liquid fumes and coming from top, and then we can get falling liquid film. So it's like this, and a few watt and liquid film come from top, and then a quenching here, quenching occurred here, and the liquid film front moves like this. But sometimes a boiling occur, and then the liquid film front is apart. And this situation is repeatedly, and the final liquid film is the completely covers the fuel rod. But we need to predict this velocity of the liquid film, falling velocity of the liquid film. So to predict the quenching velocity, we need to make some quenching model. So the quenching model is a HTC distribution near the liquid film front here. So previous research reported so various quenching model and then suggested the new quenching model. So this one is a liquid film, and here is a liquid film front. This one is a quenching point, and they reported it's kind of a heat transfer coefficient distribution like this. And here is a constant heat transfer coefficient, but suddenly zero after the quenching temperature. But the other one is it's slightly change the heat transfer coefficient distribution. And they called this region is wet region. And also this region is called dry region. And their model, their quenching model is composed of three components: wet region and dry region, and the quenching temperature. And finally, they added some heat transfer coefficient, HTC distribution. So finally, we can get kind of a quenching model. We can solve the heat transfer conduction quotient by using this quenching model as a boundary condition. But this quenching model have some problem. So one is a model assumes HTC distribution and values. So because they cannot measure the temperature distribution because they added just some couple, they can get only the local temperature data. So they cannot measure the temperature distribution. So that is why the actual heat distribution, they cannot measure it. And number two is the model did not consider liquid film condition. Actually, the liquid film is maybe repeatedly wet and dry and repeatedly, and the vigorous boiling occurs in the liquid film form. So the vigorous boiling is cause non-uniform liquid film condition, but they did not consider any the liquid film condition. Just apply some value to make the HD distribution. Our research motivation is based on the phenomenological interpretation. We try to make the new quenching model. That is the objective of my research. We set the experimental apparatus to measure the actual temperature distribution during the quenching phenomenon by forming the film. So we used silicon wafer as a high temperature wall, and then ideal film and added. Because silicon wafer is transparent against the infrared light, and the ideal film is opaque against the IR. So we set the infrared camera on the back side, and we can directly see the temperature distribution here. And the rigid film. Sorry, this schematic design is a top view. Okay. So and then silicon here, and then rigid film comes from here, and uh then we can make the following rigid film. And then we observe the rigid film condition by using the high-speed camera, and the high-speed camera and the infrared camera is synchronized. Okay. So the expected condition is like this. Initial water temperature is 225 and the maximum is 300. And the liquid flow rate is like this. So this actual for the image of the high temperature wall, and we added uh ideal layer on the surface on the sequence. Okay, camera setting is same. We try to use the same frame rate here, 2000 and 2000, and the completely synchronized as the infrared camera and the speed camera. Okay, so the next one is a calibration method. We got the infrared camera image like this. Is a actual temperature distribution like this when during the falling film from the top. And then based on this temperature distribution, we calculate a three-dimensional heat conduction quotient. And then we got the temperature distribution in the y direction. Y direction is a thickness direction. Okay. So based on this temperature distribution in the thickness in the y direction, finally we got the heat flux on the surface. Also, we can get the surface temperature from this. So based on this reduction, we try to understand the main factor of heat transfer near the ignition point. Okay, so this one is an instant heat flux distribution, infrared camera, and high-speed camera, and heat flux distribution. Okay, so we focus on here and the edge of the ignition point. We can find the nucleate boiling occurred in near surface, near the ignition point. There we can observe the high heat flux at boiling point. And then the bubbles is grossing, and then at the high heat flux area is expanded like a link. Yes. So maybe this one is depend on the thin liquid film layer bottom of the bubble. And then push it back to the liquid film, and then thin film is what's exhausted. And finally, it's completely dried out and the dried stuff is coming out. So then we cannot see any high heat flux point. Okay. So the next, we try to understand the relationship between the heat flux distribution and the hydrodynamic phenomena. This one is a high-speed camera image, and this one is the infrared camera image, and this one is the heat flux distribution. Heat flux distribution is we averaged from here to here, and then heat flux is like and z-axis here. Okay, so completely synchronized in the high-speed camera and infrared camera. Okay, this point is critical heat flux point, and previous research reported and this region is a wet region, and here is a dry region. but we added this region is called a sputtering region. Before the heat flux is almost equal zero. And please focus on this range to this movie. Okay, so in this sputtering region is wet and dry is a repeat. The condition was repeated due to the reverse boiling. So boiling occurred and the liquid film is moving down, but also after the bubble is coming out, and then completely we can see some dried position. Maybe and in sputtering region dry and wet condition was repeated. So next one is based on this experiment result, we try to make the new quenching model. So maybe sputtering region is very important to predict the quenching velocity. So here is a liquid film front. This one is 0 millisecond. The next one is 0.5 millisecond. So this part is a liquid film front, but bubble generated from here and liquid film moves a little bit. So this bubble is related to the development of liquid film front. So we compare is this bubble size and the actual average the heat transfer coefficient distribution in this area and the length. So the average one, so we cannot get so much a value of the widest of spot region, but we can get during the following week film count in one experiment, we can get so much bubble size. So we compare in this scale. So widest spot region and diameter bubble is almost same scale. So so finally, why the spot region is determined from bubble size near it from font. So based on this result, we made finally new quenching model. This one is a red line is a model, and the black dot is one of the experimental data. So this one is a wet region. Okay, and then we added some constant heat transfer coefficient. And then the next one is the critical heat flux point. We used the previous research and reported the correlation and a little bit modified. And then this one, sputtering region. We make correlation with by using a Laplace length, and finally we define this value from the experiment. And then this one is the dry region, and completely the heat transfer coefficient is almost zero. So, okay, so validation of this new quantum model. So this one is a benchmark data, and this one is a stainless steel tube, and a little high temperature in our cases. And then we validate our model. This one is a actual how to validate our model and a calculation of quenching velocity and the heat conduction two-dimensional heat conduction solved and added our quenching model and here the boundary condition. And finally, we calculate the quenching velocity and the displacement of application of critical heat point. So finally, this one is a result and wetting velocity and a calculation data, and this one is experimental result. So, and the triangle and this data is a Yamanouchi and the Duty model apply case. They have a very big error source because they didn't consider about the actual phenomena. So that is why they have a big error. But on our case, and error is a 30%. So this model is based on the actual phenomena and a near regression. So this is the conclusion and the final new weight model. So the first we found the main factor of the heat transfer is a nucleate boiling. nucleate point dominated heat transfer near between point. And the second one is we found a relationship between the heat flux distribution and the hydrodynamic phenomena. And based on two findings, finally we got it. We made the phenomenological reaction model. So finally, I just show some beautiful image of in our laboratory, and our laboratory focus on a very different some hydrogen phenomena, and to withdraw and the critical field class, and we apply the diffusion. It's also the onset and nucleate boiling. Yeah, it's a beautiful image of uh, analyzing for the some hydrogen phenomena. Okay, thank you for attention on my research today.
Wonderful. All right. Thank you so much for your talk on all these different aspects of quenching heat transfers. So first, I'll open up to the audience. So does anybody from the audience have a question? If so, please either raise your hand, or I think it's fine if you just unmute yourself and ask a question if there are too many.
Matthew,
Yes.
this is Mattia speaking. Yutaro, first of all, I have to say this was a wonderful talk. So thank you very much for taking this invitation and showing us your work.
Mm.
I have a couple of questions and perhaps a curiosity. When you do the copper, essentially it's an electro deposition of copper. Is there any process that you could use to create a structure such as this one, but on materials that have less conductivity than copper? So you basically do a plating of something which is less conductive.
Yes. So when we made a high porosity, so this one is almost 0.9 porosity, so that's why the very low thermal conductivity
Mm.
because when we use a copper case.
Okay. But can you use, for instance, nickel instead of copper, or
Yeah, of course we can use when we use some maybe already some industrial fields they use very different metals to plating method. So that is maybe we can use a different metal to make this kind of porous structure. Maybe same method.
so the block itself was copper or was stainless steel? I can't recall. The big
Yeah.
block you were trying to cool was copper or stainless steel?
What you mean in our research?
Yeah,
In
was
our
copper.
research is a copper block. But yeah, actually we directly to make the porous plate on the surface when we immerse in this block in this.
Thank you, Yuta.
Yep.
Okay. We have somebody raise their hand. Please go ahead.
Thank you. My name is Jubair, and I actually moved from Japan to US
Okay.
like this year, May. So yeah, that's a very nice presentation, and I think your model predicts very well. So I have one question is just out of my curiosity. So it's not related to the boiling, but about the IR camera results you have shown here. So previously I was trying to use this IR camera for the freezing of the droplet, and I was trying to determine the droplet temperature during the freezing process, but I was encountering lots of problems like the liquid transparency or the substrate background. So all these things were making like I I could get, the difference in the temperature zones, like this is higher or lower temperature area, but the numerical values were not correct. So yeah, I couldn't figure out how to overcome that for that application, but for this application, have you experienced some difficulties or have you used any special technique? Especially, I think it's also liquid and you might have the substrate might affect your temperature numerical value. Yeah, that's my question.
Okay.
Thank you.
Yeah, thank you for the question. Maybe the point, maybe I think 2 point. The 1 point is first we need to added some opaque layer to measure the surface temperature directly. So we added the ideal film to cutting the infrared ray because when we didn't use this ideal film, we can observe the different surface, not just the bottom of the water film layer. So maybe we cannot get uh, the correct value. So I think maybe when we want to measure the surface temperature, maybe we need to add some opaque against the infrared light. Okay. And the
So
second,
this
yeah,
ITO frame, so your boiling characteristic is changed. I mean,
ah,
because
yeah, yeah, yeah. Yeah, of course, when we add surface modification, IT film is low wettability, I think low wettability. So that's why that we added the silica film on the surface.
okay,
So to make a uniform liquid film front.
I see.
Okay, the
Thank
second
you.
point. Okay,
Okay.
a second point is
Uh,
when we measure the low temperature case, maybe infrared camera is not good for to measure the low temperature area.
I see. Thank
Okay,
you for this. So
yeah.
actually for my case, super hydrophobic contact angle changes if I do some modification. So
Uh,
yeah, that was the main challenge. Anyway, thank you.
yeah, yeah, thank you.
Great. Anybody else in the audience have a question? If not, I have a very quick one just on the model validation. So I saw your plot on the comparison of your model validation compared to, I think, a previous work. Maybe it was
Yes,
2 slides down, if I remember correctly.
yes,
Yeah, for this. Mhm.
this one, that's right.
Yeah, could you go 2 more down to slide 48, I think? Um, Yes, this one, this one.
This one.
Yes. So, okay, so you're calculating the um the the velocity, the quenching velocity, basically. This is what the validation is showing. So I was curious, you have the IR technique to show you that like sputtering region and the other things. So from your understanding of the model that you developed, what what was the what was the most important parameter that seemed to affect the quenching velocity itself? Was it the sputtering region, or were there other informations you obtained from the IR measurements and other things that also really helped with your predictive accuracy?
Okay, thank you for that question. So actually, wet region and this heat transfer coefficient doesn't so much affect against falling velocity, but this sputtering region and critical heat flux value is very important. Of course, and the temperature at CHF point here. So when we calculate the semi-conductivity equation, so of course we change the heat transfer coefficient distribution due to this temperature. So this zone, this sputtering region, also this inclination also change when we change the critical heat flux. Of course, when we change the temperature CHF. So and this one and this one and this length is very important too for the uh, to predict the accurate falling velocity.
I see.
So yeah, everyone doesn't consider about any but our model is correlation. So yeah, previous routes like this. So does consider any sparkling region, and of course, and yeah, that is why our model is have some good result.
Okay. Yeah, thank you. Okay. Any other questions from the audience?
Yutaro, maybe I'll ask another one. It's just a clarification about this word, the Japanese word quenching.
Okay.
Is that, the fact that this word is bent, does it
Depends,
depend
yes.
if you have a different cooling rate depending on the clay that you apply?
Depend on the thickness of the clay, and also change of the semiconductivity of the clay. So the quenching phenomena, the early quenching phenomena occurred on this braid zone, I think. And then so after that, this one is a mountain side, and here this side is a pyrite. So this one finally is bending. They control the thickness of the clay, and finally get this curvature and the pattern of this surface.
All right, thank you.
Yeah, thank you.
All right. Okay. If there are no more questions, I think looks like there are no more questions. I think we can thank our speaker. So thank you very much, Dr. Umehara, for the amazing talk. I also just want to make a quick announcement. So I will send a calendar invitation to the TTC mailing list after this talk. So next week we actually have another seminar. So this week it was on quenching, and then next week it's going to be with Dr. Andrea Pickle from the University of Rochester, and so she'll be talking about luminescent thermometry for I think battery applications and stuff like that. So another kind of another experimental one, and talking about thermometry techniques. So this will be on Wednesday, October 30th at 12 p.m. U.S. Eastern Time. So we'll send this information out to everybody so you can take a look and mark it in your calendars. So just wanted to make that note before we wrapped up for today.